Thank you for the introduction. Hello, today I'd like to talk about temperature-dependent modeling of silicon strain gauge-based press sensors for automotive applications. Let me briefly present the outline of today's talk. I will talk motivation and background, then describe the characteristics of silicon strain gauge-based press sensors, followed by temperature-dependent modeling, and finally give conclusion. To mitigate environmental challenges, the, the automotive industry is actively developing eco-friendly vehicles that minimize fuel consumption and eliminate harmful emissions. Among these, fuel cell electric vehicles have attracted significant attention due to their ability to generate electricity through hydrogen fuel cell. FCEVs offer several advantages, including rapid refueling, extended driving range, zero emissions, and high energy efficiency. As FCEVs move toward wider adoption, ensuring the safety and reliability of key components such as hydrogen press sensors has become increasingly important. Therefore, studying and improving sensor performance under the real conditions refueling is an essential step for the advancement of FCEVs. The hydrogen, the power source of FCEVs, is eco-friendly and highly efficient, producing only water by product. However, it also has several challenging properties, including a low boiling point, risk of explosion, and hydrogen embrittlement. Given these properties, developing sensors that ensure hydrogen safety and monitoring is critical for stable behavior and efficient use of hydrogen. Especially, the hydrogen refueling occurs at a low temperature. Hydrogen pressure sensors must accurately and rapidly measure the refueling amount under these conditions. When a sensor at a room temperature is suddenly exposed to minus 40 degrees Celsius, hydrogen, a temperature response time arises until thermal equilibrium is reached. During this period, the indicated pressure from the sensor may deviate from the actual refueling amount, which directly affects vehicle safety. This is why our study focuses on a measurement methodology and modeling approach to evaluate the temperature responsiveness of hydrogen pressure sensors under low temperature refueling. Next, I will talk about sensor structure and operation principle. At first, we used a three-dimensional X-ray CT to analyze sensor structure. This technique enables us to observe the internal components in detail without causing any damage to the device. From the analysis, you can see that the sensor is composed of diaphragm, gauge chip, main PCB, spring, upper PCB, and input and output pins. Next, silicon strain gauge chip, which are key components that converted in input pressure signal into an electrical signal. The figure on the left, you can see the gauge chip observed by 3D X-ray CT from both cross-sectional and the top view. The figure on the right is the schematic diagram of the gauge chip. The chip is two silicon gauges and the three aluminum bonding pads arranged on the glass substrate. Each gauge includes a piezoresistor made of silicon, which changes its electrical resistance in response to external forces such as pressure. I will now explain the input and output operation of the sensors. When hydrogen pressure induces deformation in the diaphragm, the piezoresistor in strain gauge detects this deformation, resulting in a change in electrical resistance. This resistance change is subsequently converted into an electrical signal, which is delivered as a signal processing IC on the main PCB. The spring, the upper PCB, and input and output pins. Overall, this process clearly demonstrates how mechanical deformation is systemically converted into an electrical output. Next, temperature-dependent modeling about conventional methods. To evaluate the temperature responsiveness of the sensor, we simulate the rapid low temperature refueling environment for the sensor. Conventional methods typically involve transferring the sensor from a room temperature bath to a low temperature bath to evaluate temperature responsiveness. It may cause inaccuracies due to unaccounted temperature variations and complicate the control of pressure conditions. So, we developed a new controlled experimental setup. Our setup consisted of temperature regulated chamber and pressure control system to precisely both regulate the fluid temperature and pressure as shown in the figure on the left. The figure on the right shows the actual experimental setup. The pressure-controlled fluid is cooled to -40 degrees Celsius by being circulated through cooling pipe inside the temperature-controlled chamber. This ensures that fluid reaches the target condition before being applied to the sensor exposed to ambient conditions. Once the fluid temperature and pressure were stabilized, the external regulating valve was opened to initiate the evaluation. Consequently, the controlled fluid was delivered to the sensors through its diaphragm under the same fluid conditions. This setup effectively replicates the sudden thermal transition experienced by the sensor during real-world hydrogen refueling. Moreover, this novel method has been filed for patent protection in South Korea. Next, this is the result of temperature responsiveness. In the graph on the left, the input pressure represents the pressure controlled in the chamber, while the indicated pressure is derived by converting the sensor's output voltage into a pressure value. When we evaluate the temperature responsiveness of the sensor, we observed a noticeable difference between the input and indicated pressure, which was caused by a temperature response delay. This delay occurs because the pressure sensing element and temperature sensing component reach thermal equilibrium at different rates. When a sensor at a room temperature is suddenly exposed to -40 degrees Celsius fluid, the mismatch in thermal transfer between these components leads to a delay. Over time, the indicated pressure gradually converts to the input pressure as thermal equilibrium is reached. To confirm the thermal origin of the delay, we conducted an additional test at -30 degrees Celsius, where the response time was shorter than -40 degrees Celsius. Finally, we quantified the temperature response time, and we analyzed the pressure measurement error data and applied curve fitting. Among several models we used, The exponential model shows the best correlation with experimental data showing exponential decay. To analogize the variability of temperature responsiveness, the same experiment was conducted with 5 samples. The parameters A and B were extracted from multi-sensor samples. The results were summarized in a table. The temperature response time was determined using a standard of definition of response time T19, which is time required for the sensor's indicated pressure to reach 90% of its final value after a change in input pressure. Additionally, the temperature response time can be defined adjusting the value based on the desired target specification. We also determine the temperature response time at the specification T-spec, assuming a pressure measurement error data of 0.5 bar. The consistency of model parameters indicates stable behavior within the measured range. Furthermore, additional experiments were conducted to investigate the pressure dependence of the model parameters and the temperature response time. The input pressure was divided into 2 distinct levels. The experiment was performed at approximately at 240 bar and 540 bar, which represent the lowest and highest pressure achievable within test setup. The evaluation was conducted separately for each pressure condition to examine potential variations in sensor behavior under different pressure levels. This result indicates the model parameters such as coefficient and temperature response rate remain unaffected by variation in input pressure, suggesting that temperature response time is independent of pressure range within the tested range. Finally, I will give you a conclusion. A methodology was proposed to evaluate the temperature responsiveness of automotive pressure sensors under low-temperature hydrogen refueling conditions. And a new experimental setup was developed to replicate rapid low-temperature refueling more accurately than conventional mass transfer method. This concludes my presentation. Thank you for your attention.